Hi, my name's Rohan.
My name is David.
Today I'll be interviewing David, who got his degree in electrical and electronics engineering from Northwestern, and then also a master's, and then he got his PhD in electrical and electronics engineering at Stanford. So to start off with, I'm going to ask you, what was your experience like when you're getting your bachelor's?
Yeah, so when I started off at Northwestern, I wasn't even interested in electrical engineering. I wasn't even focusing on it. I was actually a chemistry major, and I was in the so-called Integrated Science Program, ISP, which is a pretty unique program at Northwestern that basically exposes students to all of the sciences. So kind of gears them up towards maybe being in academia in the future, which is what I thought I would be doing even back in high school. And I thought I would be going to chemistry. But then what happened was is that as I was walking through the halls of Northwestern, I met a professor, or I saw posters of this professor named Professor Manija Rezegi, who she's very famous in the field of semiconductors and lasers. Um, I saw her posters and her work, and I decided I wanted to meet her because she seemed very famous. And at the time, also the integrated science program encouraged us from freshman year, very beginning, to do independent research, um, even as a freshman. So I was walking down the halls, and I saw the posters for this professor, and I decided I wanted to go meet her. So I met her, and then she immediately said, "I want you to come Saturday, 8 o'clock in the morning." This was literally like my third or fourth month at Northwestern back in 2012, all those years ago. And she told me to come back, and I came back 8 o'clock in the morning Saturday to meet my advisor, who I've known for the better part of the last 12 years, right? He actually moved here to California not that long ago, maybe 10 years ago. And from then I was kind of shifted from chemistry to electrical engineering because I became very fascinated with semiconductors. I didn't know what a semiconductor was. I didn't know what a laser was. I didn't know what any of these things were. But these things, these semiconductor devices, I soon came to realize, power our everyday lives. They're in our computers, they're in our phones, they're everywhere. The semiconductor is an extremely important invention, and so is the laser and all of these other things that are based on semiconductors. So, that's how I got into that. And then that pretty much dominated my whole undergrad experience. I mean, being an undergrad, you do have your experiences with the students, like, having, fun and all this kind of stuff, going out and parties like that, which we all do and we did. But yeah, I mean, just to answer that question, basically, that was my whole bachelor segue or entry into electrical engineering. Yeah.
Mhm. Once you finish your bachelor's, what made you want to move on and get a master's and then eventually PhD?
So as I was doing my bachelor's in electrical engineering and doing these projects that I was given as an undergrad, right, and working in the lab and stuff, I was just so interested in it. It's just so cool, work especially at Northwestern, we had a lot of opportunity, in that lab that I worked for with Professor Ziggy at the Center for Quantum Devices, you know, to just do good research. There was just so much equipment there. We're talking industry level equipment to the tune of tens of millions of dollars of equipment in one place that an undergrad was able to use. That's not common in most universities, right? And so I'm just like, yeah, I want to continue doing this. So I did a master's with her, and then after that I decided to do a PhD because I was just that interested in this technology. Yeah.
And at this stage, were you still interested in going into academia?
At that stage I was, yes, absolutely. I all the way up until maybe the first year of my PhD, and then I quickly realized that it wasn't for me.
Yeah. Uh, how'd you like being at Stanford compared to Northwestern?
I'm always a wildcat. I I uh this is the difference, right? Wherever you do undergrad, it's always going to be a very special experience for you. I mean, it depends on the person, but for me, I loved undergrad. I had a lot of fun. I learned a lot, and I also had a lot of fun. Then I went to PhD, and everything started to become much more serious because it's a job, and so it wasn't as fun, right? I mean, research is fun and cool and all, but it's not like the only thing you want to do. You want to have other things in your life that you want to do. You want to have you know diversity of thought. You want to not just do one thing all the time, right? And the thing about the PhD is that you're pretty much just doing that. That's your life. And so then it made Stanford kind of like, not as fun as Northwestern. Yeah,
Yeah.
I would have to say.
What was your research based around during your PhD then?
My research in my PhD was around something called nonlinear optics. I don't know. Do you know uh, um,
No.
about anything about that? Okay, so let me put it this way. Optics and photonics really is this new. It's a very fairly new field, and it's in particular silicon photonics. In fact, that's where I work for now. I work for a startup that we do silicon photonics called Light Matter. Um, Photonics is really just about the manipulation of light. You have light of different colors, frequencies that cover the entire electromagnetic spectrum. And what you would like to do is to manipulate them. And one way you can do this is through something called nonlinear optics. So you have what are called materials that are nonlinear optical that can manipulate different colors of light to produce other colors of light. So, for example, let's say you have red light and green light. You can mix them in this crystal of nonlinear material to create some other color, purple, I don't know, through different nonlinear optical processes. And well, it turns out you can do that in silicon, the same silicon that powers your phone, that powers your computer. You can do nonlinear optics in that, which is really cool. And why it's cool is because nonlinear optics also has a very interesting application of something called quantum computing, which is this term. You've probably heard of it. I don't know. Quantum computing is this buzzword everyone's talking about these days because quantum is, it's just it's a hot topic now. And it turns out you can do quantum operations and things with nonlinear optics. And if you can do it on a silicon chip, you can then have a quantum computer, just like you have a regular computer. And that's what my PhD was about, was nonlinear optics and silicon photonics.
Um, so I saw it says you spent 6 years and 8 months on your PhD. Uh, I don't know too much about it, but what kind of goes into seeing like how long a PhD takes? Because I know there's a really wide range of that.
Yeah. It's a function of your professor and the research project that you choose or are given and what's going on in your life. So I would say for electrical engineering, the average PhD is generally about 5 years, 4 to 5 years. Mine took longer because I did a very esoteric experimental PhD that was, with and a project for that PhD that was very, very kind of far-fetched, very, very difficult. It was a very difficult project. And it was very much we were trying to get something that nobody else got before. And I published on that, but it was extremely difficult. And a lot of the other PhD students in electrical engineering, and we're speaking strictly about electrical engineering here because I don't know about the other fields, but electrical engineering at least, there's different branches you can go into. You can go into signals and systems. You can go into devices like traditional transistors and things like that. There's a lot of new materials that they're trying to explore and that kind of stuff. Signals and systems is another thing. It's very mathy, but that generally is a shorter PhD because it's really just about algorithms, stuff like that. And you can segue that into like AI and things like that, algorithms and whatnot. And then there's what I did, which was much more applied physics based. It was like novel device kind of stuff, because and that kind of stuff generally takes a very long time because you have to make it work, and it's not easy.
Um, so right now you're working at Light Matter. Uh, what's your job looking like then? Are you working in person or remote?
I mean, they want us to be in the office 3 days a week, but I come in every day. Um, but my work is primarily design oriented. So I design these photonic circuits, for these photonic computer applications, photonic information processing applications, and whatnot. A lot of it's related to what I did in my PhD, and I'm at that job at Light Matter. I am a photonics design engineer is the title.
Mhm. And when you're talking about the ones that you're working on right now, how small are those?
The what?
Uh,
The what I'm
the
working on?
things, the
Oh, the circuits
sorry,
and
what?
things we're working on.
Yeah.
Yeah. Um, well, I mean, at the component level, we're talking about devices that are on the order of like tens of microns or hundreds of microns in size. But then these circuits get put into big, big chips that I'm just a part of designing them, just one part of many people who design them that are, fairly large reticles, maybe a couple of millimeters by a couple of millimeters or something like that. You can imagine a chip that's, the same size chip as the one in your computer, like a computer processor. But the components themselves, for example, the uh, different circuit components inside, photonic circuit components inside, generally on the order of hundreds of microns, tens of microns, micrometers.
Yeah. So right now, what do you think your future holds in stock for you job wise?
I think that the field I chose, which is silicon photonics, is is a hot topic, is a hot field. It's not as hot currently as AI and computer programming and all that kind of stuff that, they're paying a lot of money for. But there will come a time, and we know this because it's always a push and pull between hardware and software, especially when it comes to finances, especially with compensation. Right now, these companies are paying a lot for software. They're not paying that much for hardware. But as you can see, Nvidia, which is primarily a hardware company, they are putting out the latest cutting edge hardware, right, for these GPU chips that powers this AI revolution. So they're now getting a lot of money for it. Each GPU chip is like what, 40, $50,000. That was not the case, 10, 15 years ago. Now, what we are doing is the cutting edge beyond that. It's like our devices, the work we're doing because we're a startup is like 20 years down the line. It's actually even further down in terms of cutting edgeness. And my prediction is that, we have a good shot at making our devices and systems work and having even more powerful, let's say GPUs, you can call them. And that's going to be really good, at least for, I think, my future and the future of people in our field, silicon photonics, because we need better hardware. We need better hardware. The demand for data is only increasing. There's only going to be more people in the world that want more data. And this data is going to be a lot of bandwidth and a lot of processing power is needed for that. So we need better and better hardware.
Yeah. Right now when you're working, um, because you're saying you're designing these, is that mostly on like a CAD-like software?
Yeah, that's a good question. It's kind of like CAD. Yeah, it really is. The name of I mean, there's different kinds of software that we use. A lot of it we actually write in Python. We use Python to code these different components. Then there's a back-end engine that takes those components and draws a CAD file out of them.
Um, so a typical like day in the life of working in your job, how much of that is spent doing that versus other things?
It depends. When we have to, there are these things called tape outs where we have to submit a design to a foundry to make our chips for us. The 3 or 4 weeks before that is very intense and it's a lot of just layout. But most of the time when we're not in tape out season, I'm designing the components themselves. So a lot of that is just doing a lot of simulations and calculations and kind of footprinting. And then once we have the final design, then we lay it out into a product or a chip that will be fabricated for us by a foundry.
Also, do you know like how these foundries make these super small scale chips?
Yeah, so it depends. So for example, electronic chips, if you mean like CMOS chips, like for example, those that are made by TSMC, which is one of the leading foundries in the world for this kind of transistor technology. They are at like what 3 nanometer node or even smaller. Last time I checked, um, they use what's called deep UV lithography. That's something developed by a company called ASML in the Netherlands that makes these giant lithography machines. So lithography is a technique that you use to write patterns or structures or circuits on chips, and you can do this at scale. And ASML, through their collaboration with Zeiss in Germany, has produced this extremely expensive, complicated system that TSMC buys quite a lot of because they have the money and the time and the scale to be able to use these to make all these chips that are literally in your MacBook or your iPhone right now. Well, they use this deep UV lithography technology and a bunch of stages of mask reduction and some, a lot of optics basically to miniaturize, the size of of whatever it is that they're trying to write on the silicon chip. So you have a mask, and then you have to do a map. You have to reduce the size of the pattern as you go down in these different stages through optics, basic optics, right? But it's also a combination of the optics and also the light source that you're using. And they're using a deep UV light source because the lower the wavelength, the higher the resolution, right? So it's extremely complicated. But you should look at ASML and Zeiss and what they've done. I mean, it is a really phenomenal system, and their TSMC is leading the efforts for using these things. Yeah.
Yeah. So in electrical engineering, you're talking about how there's different fields. As semiconductors is very broad, but like a massive one. What are the other big ones?
Yeah. So in electrical engineering, um, you have signals and systems. That's one big one. So that's people who they are not even really hardware people, but they're very math people. They're very good at probability theory, and they think about algorithms. And for example, best ways to do, like for example, in the internet, the way that we communicate information is through ones and zeros. But sometimes these ones and zeros they get lost through noise in the channel, and you have to estimate based off of that noise what was the signal that this person sent me when I receive it. And there's this thing called estimation theory. That's a whole probabilistic kind of a study that can basically figure, hey, what was the thing that this guy sent me, or something like that, right? So there's stuff like this. That's signals and systems, and also not even just telecommunication systems, any kind of a signal, like even from satellites or something. Like these are all signals. How to process that information, how to manipulate it. That's a whole branch itself. Signals and systems. Then there's semiconductor solid state devices, because that was originally an applied physics thing because it's very much material science, but then it eventually came into electrical engineering because the transistor, I mean, that's such an important component. Any electrical engineer, they use that. But there are different abstractions of electrical engineering. So for example, now, okay, you have the device level people who just they focus on the transistor. Then you have people that we call them the circuit level people. They don't know how the hell this, transistor works or anything about it, but what they do know is how to use it and how to make big complicated circuits out of it. So, and amongst those people, we have what's called digital designers and analog designers. So there's analog circuit designers who design analog circuits, and there's digital circuit designers who design digital circuits. And there's something in between called mixed signal people. So the mixed signal people, they're kind of in between. So that's circuit designers. And then you have also people who do DV, design verification. They need to verify, that all of these circuits, for example, are operating properly. There's no errors whenever they run certain tests and things like that. Then there's physical verification and design. And then what else is there in electrical engineering? Those are the only ones I can think of.
Mm.
I can do a quick search and see, yeah, for example, yeah, there's a few others. Control systems. I would put that under signals and systems, but like, control theory, robotics, for example, and designing PID control loops for, those kinds of things. And then, there's another big one, power engineering. So power electronics, for example, people at Tesla, for example, they need to design these gigantic, power delivery systems, these huge transistors that can switch basically to power these motors and wheels and things like that. That's a big branch itself. And then a bunch of other things like within circuit design and that there's radio frequency engineering. So for example, designing radio transmitters, that's a big thing, not only in your phone but also for big radio transmitters and stuff like that. And then biomedical engineering, that's another big one that is a part of electrical engineering but kind of branches off into that. Yeah, that's pretty much it I can think of. Yeah.
But yeah. I think that's all the time we have for today then. Thank you for meeting with me.
For sure. Yeah, and you guys, I hope that this helps in any way. It's pretty interesting, cool that you're doing this because I guess back in my time, nobody I don't think anyone really did something like this. So that's actually one thing I want to ask you is why are you doing this actually? And if you want to stop recording, that's up to you. But I'm
Yeah.
curious to know why you start
Um,
doing this.
yeah, so a few months ago, I had contacted a bunch of people on LinkedIn just to learn about their jobs. And then I myself also want to be an electrical engineer. So that was mostly who I had contacted. And then through doing that, I learned a lot about, or actually back then I hadn't figured out I wanted to be an electrical engineer. I was also thinking about chemical. So I met with people who did both of those. And then I learned so much through it that I wanted to be able to record these and post them as podcasts so other people my age can also learn.
So why do you want to be an electrical engineer exactly? What about it do you like?
Um, Well, I've looked a bunch online, I guess, um, at basic things like job opportunities and stuff like that. And then as far as my actual interest in electrical engineering itself, is just I've done classes in school, like physics and stuff that have made me interested in it. And then I also just researched online and read a lot about that, and it seemed much more interesting to me compared to like chemical or other types of engineering.
That's cool. Yeah, you're one of the very few. I mean, most people these days they're more interested in computer engineering or like computer programming and stuff. That's where most of the money is. But electrical engineering for me is, I think it's cool, and I think you made a good choice. I think it's the most difficult of all the engineering disciplines. It is the hardest. It requires a lot of discipline and it is a lot of math. It's very hard. When I started the program in double E at Northwestern, I think we started with like probably 40 people and ended with like 15 because it's grueling. It is not easy. It is of all the electrical engineering discipline, it is the hardest, but it also gives you the most appreciation for not only physics because you do need to know a lot of physics to even do it, but also just a bunch of fields. It's everywhere. It's really everywhere. And once you understand electrical engineering, you can very quickly get into a lot of other things. Even mechanical engineering, you can get a good hold on that. But yeah, I hope this was helpful. And yeah, I appreciate you asking these questions, especially as a high school student. I hope that this helps you guys. Yeah.
Yeah, but yeah, thank you.